Hello, and welcome to our video entry to Harper University's Young Innovator of the Year Award 2014.
We are Team Talk Nerdy to Me,
And in this video, we hope to present to you our robot design, called the Fully Advanced Chef Equivalent, or FACE. Our innovation is designed to help people around the house, specifically in the kitchen. We have come up with the idea of an autonomous robot that, through the use of certain features and attachments that we decided on when putting together a list of requirements for a design specification, is capable of safely preparing a meal. Autonomy. First of all, the question begs, what is an autonomous robot? Well, by definition, an autonomous robot has to follow a number of rules. No, not the 3 laws of robotics that Isaac Asimov created for his 1942 short story Runaround, and was later used in the famous Will Smith movie I, Robot. I mean real laws that are followed by real companies who design real independent robots. The requirements for these autonomous robots are that they must have the ability to 1. Gain information about their environment, 2. Work for an extended period of time without human intervention, 3. Move themselves through their operating environment without human assistance, and 4. Avoid situations that are harmful to people, property or themselves unless those are part of its design specifications. When designing our robot, we made sure that our idea followed these rules. We will revisit these requirements at the end of this video presentation. 3D positioning. So, when designing our robot, we had to consider that it is to work in an unknown kitchen environment, and to do this, the robot must acquire knowledge of the task-relevant objects, which can include, but is not limited to, the dishwasher, the oven, cupboard doors, drawers, food objects, and containers. It must create 3D models of the environment by collecting data from scanning a room and processing this data autonomously in a way that it creates hierarchical relationship between different items and how they work together. For example, this. So, using something like ultrasound, which is what bats use for echolocation, the robots could make a blueprint of this kitchen. This would work by the robot sending ultra-high frequency sound out and timing how long it takes to get back. Using a bit of maths, it would be able to work out how far everything is from the robot at a given position, and it could string together the data it receives. After doing this from a few different spots, the robot could stitch together some digitally processed images and create a 3D blueprint that it holds in its internal storage. A section of the kitchen would appear as one object, and then it would have to be broken down into smaller objects like this diagram describes. It would categorize objects, appliances, and their parts and include the geometric information about them, like their dimensions and the functional components. Then, as it is autonomous, it would have to use existing algorithms, or, for unconventional kitchen designs, create new algorithms using artificial intelligence, with which it uses its parts to open an object. Scanning food items. Regarding food items, it would scan barcodes of the food and use the internet to figure out what the item was. For natural items such as unpackaged fruits and vegetables, it would scan them using the latest software and surface technology, which has already been tried in places in the world like Japan, who use these types of scanners to scan fruits with no barcodes. Furthermore, an inventory list of all items would have to be kept. This last feature would be especially useful, as when products run out or spoil, the robot can store a list of products that need to be replaced on its memory, and this list can be printed out. This hard copy is more commonly known as a shopping list. Tasking. First of all, when tasking autonomously, the cooking robot would need to be able to do basic cooking tasks, such as mixing and stirring, as well as cutting. Furthermore, depending on the type of food it is handling, it would need to decide the force and method of carrying out individual tasks. For example, you'd need to stir a cake mix a lot more vigorously than you would mix a salad. The robot would also need to be able to use small equipment, like the knobs on a gas hob and the latch on a toaster. Part of our requirement of the robot was that it would be able to do the preparation for the cooking, like getting the correct quantities of each ingredient. We figured the best way to work this out would be if the thumb of the robot, i.e. underneath whatever was being poured, would have the necessary capabilities to weigh the product, so it can work out how much of the food has been poured into the mixture. Also, as a robot, it wouldn't get impatient, so it wouldn't tip the jar or whatever it is pouring too far, which, let's face it, we've all done. The robot should be able to use the list of products and quantities of the remaining products and cooking websites online to find a recipe. These websites let you input whatever ingredients you have and will find a meal for you. A lot of these sites allow you to set search criteria, so whether you have a hankering for Chinese food or just a good old burger, this robot can find the ideal meal for you. Graphical user interface. Like most machines, the user would have to have some input. For example, turning the robot on and off via a power switch. The robot, as it would have to use the internet to find recipes, would need to connect to Wi-Fi. Now, I'm sure you know the struggle of connecting to Wi-Fi. When you open the connection screen, there's a plethora of Wi-Fi names, and unfortunately, most of them are secure. Well, when you connect to your own Wi-Fi, you at least know the information required to connect, and you would need to input this information to the robot. This would require a user interface, specifically a graphical one, so you can select the correct wireless connection, and you can enter in a password. Another important use for the graphical user interface is so you can select whatever recipe you want, which would all be stored on the robot's internal database. This would be easier and more practical than having to program the recipe in, as well as the fact that it allows you to browse recipes yourself. Self-maintenance. This robot is clearly smart, so why should it not be able to have some control over itself to use its artificial initiative? We thought of this and we decided that it should be able to maintain itself, whether it is a matter of protecting itself from damage or just keeping out of the way when it is not in use. The robot is designed to move around, especially in the kitchen, so it needs a method of transporting itself. The most common, basic and efficient way to move something is through the use of flat-sided, round-edged objects, known as wheels. Instead of using conventional wheels, like you'd find on a bike or even a car, you would use spheres instead. This is useful because combined with special gyroscopes, these wheels can roll, like they would with a motor. This is better than using conventional motors because they don't need to be connected via wires. They can use Bluetooth, and they can turn on a radius of 0. This means that they can turn on the spot, rather than having a large turning circle like a car. For vertical movement, the robot would need to have a scissor lift-like mechanism above its wheels, but underneath its body, so it can reach task-relevant objects at different levels. Don't you just hate it when you put your phone or another appliance on charge, but you forget to turn the charger on? Well, our robot would have the capability to plug itself in and turn itself off when it is finished cooking. Using the 3D mapping, the robot would be able to locate a main socket and would remember the exact location of it relative to permanently placed objects in the kitchens, like cabinets. It would wheel itself over to the socket and unravel just enough of its charger, which would plug into the main socket and would ensure that the socket is on. If it was charging, the robot would set itself to standby and would remain off until it regained full charge. When this happens, as the robot would just be on standby, it would power up and turn off the socket, put away its wires, and then power down completely until its next usage. Now, we all know that cooking can get a little messy, especially when you're just a robot. This is why the robot should be water resistant. This means if a little water, or most other cooking substances, was to splash onto the robot, it wouldn't malfunction or break, which would be less than ideal. It would also be quite helpful for the owner of this magnificent robot if the robot were to clean itself up if any sauces or anything managed to splash onto this automated machine. Safety. The most common safety issue with cooking is fires. That is why the specification for our robot includes a section about safety with fires. Our robot would have fire detection capabilities inbuilt as standard. In the event of a fire, our robot would analyze the surroundings and the base and the source of the fire in order to deduce the cause of it. It would also work out the possible dangers near the fires. For example, if there is oil, its main priority would be to move the oil, or to take measures to keep the fire from reaching the oil. Also, using whatever hazards there are, the robot would figure out what the safest way to put out the fire is. This is important because if there are lots of electrical appliances around, for example, you don't want water attempting to extinguish the fire, as we all know from our days in primary school that mixing electricity and water does not end well. The robot could notify you via text, and if the fire was to get out of hand, it could notify the emergency services. Depending on your needs, you could get adaptations of the robot, so with one possible package, you might want the robot to also tweet a picture of the fire, so you have a digital copy of it and all your friends know about it. Possible developments. A possible development of our robot design could be that you can tell the robot how quickly you need a meal made, so if you are running late, the meal can be made fast enough so you have just enough time to squeeze in a quick meal. You could also text the recipe into the robot, and it would make whatever you want in time for when you get home. For this, you would need to store a copy of the database on your phone, or you could have a web page with the database accessible on it. You could just text the robot the reference number of the recipe, and would use the database to figure out what you want made. If the robot was off while you're out, when it receives a text, it could power up automatically, so there is no need to leave your robot on all day. For these ideas regarding texting your meal in, the robot would need to have a SIM card. Conclusion. To conclude, the specifications that we needed to meet for the robot were that it would be autonomous, utilize 3D positioning through scanning, have built-in safety features, and be mobile horizontally and vertically. Our robot is autonomous because it follows the 4 laws of autonomy, because 1. It uses 3D blueprinting and scanners to learn about its environment. 2. It has all of the algorithms programmed within it to work and can put itself on charge and power up or power down itself. 3. It can move itself through a kitchen by referring to its 3D blueprint. And 4. It cannot hurt anyone and should not damage anything. We would like to thank Harper University for giving us this opportunity. We hope you enjoyed the video. Thanks for watching.